Okay, hello everybody, and let me talk to you a bit about Gabriel's horn. So first, let's explain how this thing is defined. It's defined by taking the function 1 over x, and we're taking it from x equals 1 up to infinity. So this part of the function we're going to use. And then we're going to revolve it around the x-axis to get this horn. I've drawn it up here. This is what it would kind of look like. Of course, it would extend infinitely long in that direction. Okay, so what's so special about this horn? Why would we talk about this construction? Well, there's a kind of paradoxical structure going on. It has to do with the surface area and the volume of this shape. So let's first find the volume of this this horn. So by doing that, we're going to calculate the volume from 1 up to some number a, and then afterwards we're letting a run towards infinity. So what's the volume gonna be? Well, the volume, and remember it's for a single circle, it's pi r squared. So the volume of revolution, integral from 0 to a of this function squared. So the function squared will be 1 over x squared dx. And well, we can calculate this. This is going to be pi, and then we have negative 1 over x from, oops, should have been a 1, going from 1 to from 1 to a. Evaluating at a gives negative 1 over a, and evaluating at 1, and we have to subtract that, so the negative cancels and 1 over 1 is 1. So this becomes pi times 1 minus 1 over a. Okay, so that's a nice expression. Now we want to let a run towards infinity, so the limit as a goes to infinity. Let's make this volume sub a to indicate that we're letting this run towards a. This is going to be, well, limit of a to infinity of this quantity, pi times 1 minus 1 over a. And there's only one a inside, and we can, if a goes towards infinity, this goes towards 0. So we're just left with pi. So the volume of this horn is pi, and it's quite nice. But what's the most important part is that it's finite. So I'll indicate it by saying it's less than infinity. So let's call this the volume. Okay, that's quite reasonable. There's nothing paradoxical about that. But now we're going to calculate the area. And let's first calculate the area up to some point. So that's going to be 2 pi. And then we have the integral. And remember, it's when you're doing such an area of an of such a rotated object, then the area in general is going to be, let's write it down here, 2 pi integral, whatever the bounds are, and then the function of x multiplied with the square root of dx over dt squared plus dy over dt quantity squared. So I guess this should have been a t as well. So remember this, and applying this to our integral yields this complete integral from 1 to a. Then we have our function 1 over x, and then we have this square root differential of x with respect to x in fact, because that's how this thing is defined. Yields just 1, and 1 squared is 1, so we just have a 1 up here. And then we have to differentiate our function y with respect to x. So that's just going to be negative 1 over x squared and squared. And I'll integrate this with respect to x. Okay, so you might look at this and say, yeah, well, it's kind of a hard integral. And it actually is. So we're not going to explicitly compute it up here. You might as well just do that and then conclude, then make the same conclusion. But we're going to make an inequality up here. So this is most definitely bigger than, well, this is a square, so it's bigger than or equal to 0. So we can just drop this term to make something smaller. And so we can the square root of 1. Square root of 1 is 1, so this is just the integral of 1 over x. And the integral of 1 over x, that becomes negative 1 over x squared. The natural log, of course, of x from 1 to a. Natural log of 1 is 0. Natural log of 0, natural log of a is natural log of a just. And we had this 2 pi again. So we just get that this is 2 pi natural log of a. Okay, that's quite interesting. Because now we say the area, which is equal to the limit as a goes toward infinity of the area up to a, which is the limit a goes to infinity of 2 pi natural log of a. Well, this quantity, a natural log of a, gets arbitrarily large. So in fact, this is infinite. So we can just informally say that this is infinite, and it's not, infinity is not really a number, but we don't care about things like that at the moment. It's at least unbounded, it goes towards infinity. So this object that we have, this horn, I'll make a quick picture again. Its volume is finite. It's pi units. So we can just, for example, we can fill it with paint, although we cannot paint the surface. And because the area is infinite. And that's the paradox about this horn. It's quite strange, because you might think, well, if you fill it, then you actually do paint the inside. Well, actually that's true. So this isn't really a paradox. It can be easily solved by remembering that you can actually paint an infinite surface with a finite amount of paint, just if the paint gets thinner fast enough, which it does by this. This thing gets really small quite fast. So it looks like a paradox. but it actually really isn't. A funny detail, you might wonder, is it possible, and now the area is infinite while the volume is finite, could the converse be true of a certain object? Could the volume be finite but the area be the volume be infinite but the area be finite? And it turns out that's actually impossible. So that's a nice fact to end this video with.